So this is Griffiths Quantum Mechanics, problem 5.23. What we've got are three particles in thermal equilibrium, but they're not interacting, however you work that out, in a one-dimensional harmonic oscillator potential. So we'll just draw this real quick. So here's our potential. It's a parabola, right? We got three particles in there. Okay. Okay, so the total energy is 9/2 h bar omega. Okay, so we're going to be looking at how do we divide up this total energy among these three particles, and what are the probabilities of the different states and so on. Okay, so let's see what we've got. The possible occupation number configurations. How many distinct states are there for each one? What is the most probable configuration? If you picked a particle at random and measured its energy, what values might you get? And what is the probability of each one? And what is the most probable energy? Okay? Alright, that's a lot to worry about. But first, let's just look at how this can be divided up. Alright? So, within the harmonic oscillator, we know that each particle, so if I write E sub 1 for one particle, right, it can be n plus 1/2 times h bar omega. So there's always going to be 1/2 of this, 1/2 h bar omega, right, which will be given to each particle no matter what. It's like the 0-point energy. So it's this term right here. Okay, so we have so 3/2 h bar omega go to 0-point energy. Okay, so that leaves 3/2. Well, let's just write this out. 9/2 minus 3/2 equals 6/2 equals 3. So we have 3 h bar omega to still decide what to do with. All right, and the quanta. All right, we might, if we were to draw in the energy levels here, we start with 1/2 h bar omega, but then we go in steps of 1 h bar omega. So 3/2 h bar omega, 5/2, right? Okay, so basically we have 3 h bar omega to work with, and it's quantized into units of h bar omega. Basically we have, it's like we had 3/4 and we're dividing it among 3 different people. Okay, how many ways can we give each of them a quarter or a dollar or whatever you want to think of? Okay. All right, let's see. So what are the possible occupation number configurations? Okay. So we're looking at distinguishable particles first. All right. So right off the bat, the first one we can think of is, let's give each particle 1 h bar omega. In addition, right? In addition to their 1/2 h bar omega, which they already had each. All right. So what this means is that each has. So when I write 1, 1, 1, that's dividing up these 3 quanta, and it's actually 3/2 h bar omega for each one. So we'll just keep that in mind, but I'm not going to keep writing all this h bar omegas and different things, too much writing. Okay, so when I say 1, 1, 1, that means 3/2, 3/2, 3/2. So when I say, if I say a 2, that means 5/2. Okay, so you always have to add on the 1/2, you know, if you, and then multiply the whole thing by h bar omega if you want to get the actual energy of this. The way I'm looking at, we're just dividing up these 3 quanta. Okay, So here we go. So here's one way to do it. All right. Another way to do it would be, suppose one of these had 2. Well, we only have 3 to give. That means another one must have 0, and the last one must have 1. Okay, so this is another way to divide them up. But since they're distinguishable particles, this is a different state from, say, 0 to 1. Okay, so there are 6 of these different combinations. Let's see, which ones am I missing? So I need a 2, 1, 0. Okay, I need a 1, 2, 0, and then I'm missing 2 more. That's a lot of little commas. So I have 2 in the first place twice, 2 in the second place twice. I need a 0, 1, 2, and a 1, 0, 2. All right, so there are 6 ways, since we're talking about distinguishable particles, that this can work out. All right, we're just working this out real quick, and then we'll get to how Griffiths asks us the question, and how we can get the answers from this. Okay, so here's one way to divide them up. Here's 6 more ways to divide them up. Each of these is basically the same, with 2 given to one, 0 given to another, and 1 given to the third, just in different order. Okay, and there's one more way, which is to give all of them to 1 and 0 to the other 2. And again, since they're distinguishable, this is different from if we gave it to this middle guy, or if we gave it to the third guy. Okay, like this. All right, so there's 3 ways to do this. Okay, so now that we have this sort of thing down, let's look at Griffiths' questions. So, what are the possible occupation number configurations? All right, so the way Griffiths would do this, the way he writes this is, we ask, like, how many have 0, how many have 1, how many have 2, how many have 3, all right, and this, that's as high as we need to go, so, because the highest number we see in all of these is 3, okay? So, let's look at this one first, right? This has 3 with n equals 1. So what this would look like is, let me write these on a separate sheet, right? So this configuration right here, we would have 0, and then we have 3 of them, 3 1s, right? We have 0 2s, we have 0 3s, and nothing else. Okay, so that's that configuration. This configuration, well, we have 1 0, we have 1 1, and 1 2, and 0 3s. And then this configuration, we have 2 0s, we don't have any 1s, and then we have 1, wait a second, 2s, right? We have 0 2s, and then we have 1 with 3. So here are the, what are the possible occupation number configurations? Here's what they are, okay? And again, these are just those quantas. So if you wanted to know the energy, these ones would have h bar omega over 2. These would have 3 halves h bar omega. These would have 5 halves h bar omega, and these would have 7 halves h bar omega. All right. What are the possible occupation number configurations? They're these. How many distinct 3-particle states are there for each one? All right. How many distinct 3-particle states are there for each one? All right, so this one, there's only one way to write that, right? So when distinct 3-particle state. Okay. All right, and then for this one, 1, 2, 3, 4, 5, 6. There are 6 of those. 6 distinct ways of writing this configuration right here. 6 distinct 3-particle states. And then this last one, we have 1, 2, 3. So, right? Okay. What is the most probable configuration? Well, it's this one right here. Okay. I'm just going to draw a little arrow. The most probable configuration. If you picked a particle at random and measured its energy, what values might you get, and what is the probability of each one? All right, so here we go. I'm going to go back and look at these guys right here, okay? Because these are all of the possible states available to our system, right? So, the different energies we can measure are h bar omega over 2, 3 halves h bar omega, 5 halves h bar omega, and 7 halves h bar omega. Okay? So when we look up at these numbers, what these numbers are 0, 1, 2, and 3. All right, so the question we're asking, if you picked a particle at random and measured its energy, what values might you get? So these are the values we might get for the energy, right? In order to find the probability of each one, we're going to look at all these possible states, and we're going to pick out how many times does each one of these numbers appear, okay? So, number of occurrences, whatever, and if we look at all the states, right? All right, so we look at 0. Draw arrows just to keep these straight. Looking at 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 different of these, 12 of these. So how many are there? There's 6, 9, 10. So there are, so out of these single particle states, if we pick a 0, which means if we measure h bar omega over 2 for the energy of a particle that we pull out of the bag, there are 12 different ways that that could have happened. We could have picked this one, we could have picked this one, we could have picked this one, we could have picked this one. So we don't know what the other energies of the particle are, the other 2 particles are, but they would either have to be a 2 and a 1, or a 3 and another 0. Okay. For those numbers, which corresponds to 5 halves h bar omega and a 1 half and 3 halves h bar omega, or another h bar omega over 2 and a 7 halves h bar omega. All right, same thing for this one here, which corresponds to measuring an energy for the particle that we draw of 3 halves h bar omega. So let's count the ones. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we just have 9. And then we count the 2s. Here's 1, 2, 3, 4, 5, 6. And we count the 3s. 1, 2, 3. There are 3. All right, so here we go. So here's the values we might get for the energy. In order to get the probability for each one, we need to just normalize these. So we just divide them all by the sum of all of them. So what do we have? 6 plus 9 is 9, plus 9 is 18, plus 12 is 30. All right, so if we want to get the probability of each of these, we just divide by 30. Okay, so here are the probabilities of measuring each of these energies. Okay, and then what is the most probable energy? And it's this one up here. 12 is the largest number here. 12/30 is the largest number for our probabilities. So the most likely energy is 12. We'd pick a 0 and we'd measure h bar omega over 2. Most likely energy is h bar omega over 2. All right, so now let's look at the case of identical fermions. So we're on to part B. We're going to be ignoring spin. So all we have to do is, let's just come back to where we wrote these states, and let's just see how this would be different for fermions, okay? So part B, fermions. Ignore spin. Okay. So what do we know about fermions? Well, the Pauli exclusion principle says that we can't have any two of them in the same state. So, so for this, since we're ignoring spin, you can't have like two of them on this energy level, one spin up, one spin down, right? We're ignoring spin. Basically, you can't put any two of these particles in the same energy level. So that kills this one, right? Because we can't have three particles in one energy level. And it also kills these guys down here because we can't have two of them in the ground state at once. All right, so there's only one option, which is, it's 2, 0, and 1. I'm just going to write it 0, 1, 2, just to put them in ascending order, okay? So this is our only option. So let's see, what are the possible occupation number configurations? Well, what this corresponds to, we say how many zeros are there? There's 1. How many 1s are there? There's 1. How many 2s are there? Oop, I wrote a 2. Okay, there's 1, 2, okay? And there are 0 3s and 0 of everything else, right? We can't even reach those energies anyway with what we have. Okay, so there is only one possible occupation number configuration. How many distinct three-particle states are there? Okay, for the case of distinguishable particles, we could say, you know, giving 2 quanta of energy to this one is different from giving it to another one, and different from giving it to the third one, and so there's 6 different ways we can divide this up. When we have identical fermions, right, we can't distinguish them, we can't tell them apart, so there is no way to, you know, we can't say we're giving 2 energy, you know, 2 extra energy quanta, right, to this one and not to this one. We can't tell them apart. So this is all we've got. We don't have these 6 different ways of doing it. All we can say is there's one with 0, there's one with 1, there's one with 2. Okay, this is the only configuration that we have, and this is there's only one way to do it. What is the most probable configuration? It's this one with 100% probability. It's the only configuration that we have. Okay? If you picked a particle at random and measured its energy, what values might you get, and what is the probability of each one? All right? So if we do just like we did before, what values might we get? Well, we can get a 0, a 1, or a 2, and that corresponds to energy of h bar omega over 2, 3 h bar omega over 2, and 5 h bar omega over 2. So here are the energies that we can get. What is the probability of each one? They each appear only one time. So if I draw the same arrows that I did, like number of occurrences, right? There's only one 0, there's only one of those, there's only one of the 2's. And then we sum these up, we get 3. So for our probabilities, we have 1/3, 1/3, 1/3. Okay. What is the most probable energy? They're all equally probable. All right. We'll get h bar omega over 2, 3 halves h bar omega over 2, or 5 halves h bar omega over 2, and they're all equally probable. Okay. So fermions, you can see the case is quite a bit simpler from the distinguishable particle case. Now let's move on to bosons. Again, ignore spin. Okay. And they're also identical. All right, let me write identical up here, even though it's too late. Okay, so if we go back and look at our possibilities here, what do we know for bosons? Well, for bosons, we can have multiple particles in one state. They can all be in the ground, they can all be in one state, whatever. And in this case, they can't all be in the ground state because you have to have a total energy that's greater than the ground state energy. But if we cooled it all the way down, right, they'd all go into the ground state and condense and all that stuff. All right, so for fermions, we went through and we say these ones are no good because there's 2 zeros, and this one's no good because there's 3 ones. That's not the case for bosons. However, we are dealing with identical particles now, not these distinguishable particles. So these 6 states, we can't tell them apart. We can only count them as one. All right? And these 3 states, same story. We can only count them as one because we can't tell the particles apart. So I'm going to write the possibilities here. We have a 1, 1, and a 1. Okay, and again, I'll just write these in ascending order just for 0, 1, 2, and then a 0, 0, 3. These are the only 3 possible 3 particle states. So what are the occupation number configurations? We had 0 zeros, we have 3 1s, 0 2s, 0 3s, and 0 everything else. This one we had 1 0, 1 1, and 1 2. Didn't write the 2 this time. There we go. And for this one, we have 2 in the 0. There are 2 zeros here. 0 1s, 0 2s, 1 3. Okay, so here are our possible configurations. There's only one distinct 3-particle state for each one because our particles are identical and non-distinguishable. What is the most probable configuration? They each have one possibility. They're each equally likely. All right. The way we were weighting these before, we were counting these up, right? There were 6 ways to get this one and 3 ways to get this one, only 1 way to get this one. In this case, we only have 1 way to get each of these. So they're all these 3 configurations are equally likely. If you picked a particle at random and measured its energy, what values might you get, and what is the probability of each one? Okay, so for energy, we have zeros in here, so we'll have an h bar over 2 omega. We have ones, so 3 halves h bar omega. 5 halves h bar omega for this 2, and 7 halves h bar omega. So we can measure all the way any one of these 4 values. These are when you say if you pick a particle at random and measure its energy, what values might you get? You might get these ones. What is the probability of each one? All right, so just as we've done in the previous 2 cases, we're going to say what numbers do these correspond to? This corresponds to 0, 1, 2, and 3. And now we are going to count how many times these appear in the states that we have, right? So these right here, how many times do they appear? 0 appears 1, 2, 3 times. 1 appears 1, 2, 3, 4 times. 2 appears once, and 3 appears once. All right, if we want the probabilities, we sum these up, so 3 plus 4 is 7, 8, and 9. So this probability is 3 over 9. This probability is 4 over 9, 1 over 9, and 1 over 9. All right, so here's the energies we might measure. Here are their probabilities, and the last thing we want to know is what is the most probable energy. So we just look for the largest number here, and it's 4 ninths. So the most probable energy is 3 halves h bar omega. All right, but you're still measuring that less than half of the time, but you know there are 4 things you can measure, and you still get this one more than any of the others.